Hey everyone, and welcome. So if you've ever built a machine learning model that worked just perfectly in your notebook, but then you kind of hit a wall wondering how to get it ready for the real world, well, you are in the exact right place. Let's dive in and really bridge that gap between a cool prototype and a rock-solid production system.
It really all boils down to this one question. It's not just about knowing the different algorithms, right? It's about how you write the code that brings them to life. The real difference is in building systems that aren't just correct, but are also fast, scalable, and super robust.
Right, so we've got to move beyond that classic excuse, well, it works on my laptop. Production-level code, the kind that powers real products, it stands on three main pillars. It has to be fast, it has to be scalable, and it has to be safe from all those sneaky bugs that can completely ruin your model. And we're going to break down every single one.
First up, let's talk about speed. Think about it. A model that takes 10 minutes to make one prediction is basically useless in most real-world apps. The secret to making Python fast isn't about ditching it for another language, it's about becoming a master of the tools you're already using.
So the number one absolute golden rule for performance is vectorization. Instead of telling Python, hey, do this to the first thing, then the second thing, then the third, with a for loop, you just give it one single command to run on the entire array. What's happening under the hood is that libraries like NumPy are running this in super optimized, pre-compiled C code, which is just worlds faster.
And this right here, this is the perfect picture of what I'm talking about. On the left, you've got the classic Python loop. It works, sure, but it's kind of clunky and slow. And on the right, that's the vectorized version. It's clean, it's easy to read, and it is just unbelievably faster. You're just telling NumPy, hey, square this whole array, and it just does it.
And look, we are not talking about a small boost here. We are talking about code that can run anywhere from 100 to 1,000 times faster. That's literally the difference between a calculation that feels impossible and one that's done in the blink of an eye. It is, without a doubt, the single most important trick for performance in numerical Python.
Okay, so if vectorization is the powerful engine, then broadcasting is the magic that lets that engine work on really complex problems. It's basically NumPy's smart set of rules for handling math between arrays that have different shapes. It cleverly stretches the smaller array to match the bigger one, but without actually using up more memory to make copies. It's genius.
And here's the thing, you're probably already using broadcasting all the time, maybe without even realizing it. Everyday tasks like feature scaling, where you subtract the mean from a column, that's broadcasting. Calculating all those distances in k-means? Broadcasting. Normalizing layers in a neural network? You guessed it, it's all powered by broadcasting.
All right, that's speed. But that brings us to our second pillar, scale. Being fast is great, but what do you do when your data set is so enormous that your computer just gives up trying to load it?
Okay, so this is a classic problem, right? You get a new project, a massive data set, and your trusty laptop with 16 or 32 gigs of RAM just throws its hands up in the air. The answer isn't always go buy a bigger computer. It's about being way smarter with the memory you already have.
Just look at this table. It shows the absolutely massive impact of a few simple tweaks. By default, pandas might use a huge 64-bit integer for a user ID when a 32-bit one would be more than enough. For a billion rows, that one tiny change just saved you 4 gigabytes of RAM. And even better, look at the country column. Changing it from a generic text object to a category type, it can shrink its memory usage by over 85%. That's a game changer.
And for those truly monster datasets, you just stop trying to load it all at once. It's that simple. You use what's called chunked reading. You just tell pandas, hey, load the first 100,000 rows. You do your processing on that little piece, then you load the next 100,000, and so on. At the end, you just stitch the results together. It lets you process pretty much any size dataset on a totally normal computer. Okay, finally we get to the third pillar. And this one is probably the most subtle, but honestly, it might be the most important one. Safety. Because a model that's super fast and can handle tons of data is still completely worthless if its predictions are wrong because of some hidden bug.
And the most dangerous, most venomous bug in all of machine learning is something called data leakage. Think of it like a subtle poison that just ruins your whole experiment. It's what happens when your model accidentally gets a little sneak peek at the answers, the test data, during training. It leads you to believe your model is incredible, when in reality, it's going to fall flat on its face in the real world.
And the thing is, it's so easy to do by accident.
A classic mistake is fitting your feature scaler, like your standard scaler, on the entire data set before you split it into train and test sets. That means your training data is being scaled based on information from your test data. That's a leak. Other common ones are creating features about a user that include their future behavior, or using data that just won't be there when you actually need to make a prediction. So, how do we stop this from happening? You can't just rely on being careful and trying to remember all the steps. You need to use programmatic guardrails, tools that force you to do the right thing. And the absolute gold standard for this is the scikit-learn pipeline. What a pipeline does is it bundles up all your steps, your data cleaning, your scaling, your feature engineering, and your actual model into one single object. Then you call .fit just once and only on your training data. The pipeline automatically learns all the right parameters from the training set and locks them in. So later, when you give it your test data, it applies those exact same steps, guaranteeing you can't have any data leakage. It's like a safety net for your whole process.
All right, we've covered the 3 pillars. So now, let's put this into practice with a quick rapid-fire review. We'll hit a couple of classic interview questions that test these exact concepts. You ready?
Here's a classic one. This trips up so many people in interviews. They both work on groups of data, but what they spit out is totally different, and knowing which one to use is absolutely key for good feature engineering.
Okay, here's the simple way to remember it. You use .apply when you want to squish each group down to a single number, like finding the average purchase amount for each user. You get one number per user. You use .transform when you want to create a new column that's the same length as your original data. So you'd calculate that same user average, but then you'd broadcast it back to every single row belonging to that user.
Ooh, okay, this one is the final boss of broadcasting questions. A junior developer would immediately start writing 2 nested for loops. A senior engineer, they do it in one single elegant line of code. And boom, there it is. By using none to cleverly insert a new axis into each array, you force NumPy to broadcast them. It basically creates a grid and calculates all of the differences between every point and every centroid, all at once. This one line does the entire job. It's fast, it's clean, and it proves you really get how NumPy works on a deep level.
And that's it. Those are the 3 pillars that will take your code from being a simple notebook experiment to a true production-grade machine learning asset. Speed, with vectorization in broadcasting. Scale, with smart memory management. And safety, with pipelines. So the only question left is, which one are you going to focus on in your very next project? Thanks for tuning in.